If you were physically present in class on Friday, then you already have a handout with all of these examples written on them, and you should already have done the vector example problems. If you were not here in class on Friday, then you need to get a separate sheet of notebook paper, and you're going to just write out the problems as they appear. So please make sure that you're writing the whole question, the whole problem itself, and also then working out the answers. So we're going to start with some vector addition practice. So let's say we have these two vectors right here, and these vectors can represent any vector quantity. So it could be acceleration, it could be displacement, it could be velocity. If you remember from your notes, you can add vectors in a whole bunch of different ways, but the main thing is that you not change their direction or their length, because these arrows are just pictures that represent actual quantities. Really what we're doing is just putting pictures on what we've already been doing for a while. So what we have here are two arrows that represent any vector quantities. And you can add these in a number of different ways. And when you add them up, you get what's called your resultant. Basically, where did you start to where did you finish? It's that straight line from beginning to end without worrying about anything that's in between. The thing to remember, most importantly, when you're adding vectors, you cannot change their length, you cannot change their direction. So you have to always keep them the same as they are when you first see them. So let's look at this first example. I'm going to just repeat this first vector, this first arrow, and then I want to add the second one to it. And I'm going to use the head to tail method. So I'm going to take the second arrow and I'm going to notice I didn't change the direction, I didn't change the length. All I did was place it to where the head of the second arrow was touching the tail of the first. Then I'm going to draw in my resultant, which starts at the open tail end and is a straight line pointing at the open head end. So notice how I've got my arrow, the point on my arrow is over here. This will be the only time you ever have two arrowheads touching each other, is when it's a resultant. So you can add these two together any other way you like. You can put this shorter arrow, the one pointing down and to the left, you could put it up here to where the tail is at the head of this second arrow, and your resultant would still be the same length and in the same direction. Now let's look at this example where we're adding three different vectors. And the simplest way, honestly, would be to take this first arrow or this first vector and attach it to the tail of the second one, and then take the third one and attach it down here to the head of the second one. And that would absolutely be correct, and you would end up with a correct result. But I want to show you a different way, just so that you can see it really doesn't matter what order you put them in, as long as you don't change their length or their direction. So I'm going to start with this long one, and then put the horizontal, and then put the third one right on the tip of that. So I've connected all of my vectors. I'm going to draw my resultant starting from the open tail end in a straight line to the open head end, just like that. And hopefully you can kind of visualize, if you were to move these red arrows around into a different arrangement, as long as you don't change their length or direction, you're going to end up with this green arrow, this resultant, being the same no matter how you put them together. And the third example, again, you can do the head to tail method and take this long one and then attach the short horizontal one at its head. But I'm going to go through the parallelogram method for you real quick, just so that you can see, again, that it doesn't matter which one you use, you're going to end up with the same resultant no matter what you do, as long as you do it correctly. So I'm going to attach my two vectors at the tail this time, and then I'm going to add in my kind of imaginary lines that are parallel to my two vectors to create this four-sided parallelogram. My resultant then will start at the connected tails and go in a straight line pointing at the opposite corner, just like this. And again, hopefully you can see if I were to take this short horizontal arrow and bring it down and attach it to the head of this other one, our resultant would be exactly the same. Next thing we're going to do is practice with the Pythagorean theorem. Hopefully you remember this from math class, so I'm not going to go through it too slowly. But remember, Pythagorean theorem is a squared plus b squared equals c squared. So you walk 3 meters directly north, and then 5 meters directly west. So we're going to draw in our vectors, our arrows, and notice that the 5-meter arrow is longer than the 3-meter arrow because they do represent the magnitude. And then I'll go ahead and draw in my resultant. I want to know how long is that and in what direction is it pointing. So in this case, c squared would be r. C is r squared. So a squared plus b squared. So 3 meters squared plus 5 meters squared. Do the work. 9 meters squared plus 25 meters squared gives me 34. But we're not finished because I don't want r squared. I want r, or c, when we're looking at the actual equation. So it's going to be the square root of 34 meters squared. Still not finished. Never leave this as your answer in physics class. We're going to round it to 5.8 meters, and we know the direction is northwest. One more Pythagorean theorem example. You drive 100 kilometers south, then 50 kilometers west. And I'm going to draw my resultant in. We know that we're going to be heading southwest, but I want to know how long this resultant displacement is. So again, r squared equals 100 kilometers squared plus 50 kilometers squared. And when the squared is outside the parentheses, you square your units as well as your number. So 10,000 kilometers squared plus 2,500 kilometers squared gives us 12,500, and we need to take the square root of that, which ultimately rounded is going to give us 112 kilometers, and we also know it's going to the southwest. So now we're going to get into some projectile motion examples and a couple of things that I just want to recap really quickly about horizontal versus vertical motion. They are combined when we're talking about projectiles, but they're actually separate calculations. The only thing that connects them is the time. The time it takes to go the horizontal direction is exactly the same as the time it takes to go the vertical direction. And that's the only place that they are connected. Otherwise, they are completely separate pieces of motion. So here's our question on the left. You're preparing breakfast and slide a plate on the countertop. Unfortunately, you slide it too fast and it flies off the end of the countertop. The countertop is 1.25 meters above the floor and the plate flies off at 0.74 meters per second. Our first question here is how long does it take to fall? So we know how long is looking for time. The first thing that I encourage you to do when you have a projectile motion problem is to draw a little diagram. So here's my counter, and notice that I'm putting my distance here, my displacement, as negative 1.25 meters. And that's because we're measuring from the top down to the floor. And remember, anytime we go down, it's negative. Anytime we go up, it's a positive. We know, and here's my plate, we know the plate is flying off of the counter at 0.74 meters per second. When something slides off the counter, we know that it's sliding horizontally, so we know that that's our horizontal velocity. So let's see what we know. We're going to go through the guess method here. I'm not going to write out GUESS, but the process is going to be the same. Now, the very first thing that you know in every single projectile motion problem is that A is equal to negative 10 meters per second squared. Your acceleration due to gravity is a given every single time. You don't even have to, it doesn't have to be written in the problem. You don't have to wonder about it. You don't have to look it up. It's a given on every single problem. A is equal to negative 10 meters per second squared. We know that our dy, the height of our counter, is negative 1.25 meters, or it's falling a distance of 1.25 meters down toward the floor. We know that our Vx, our horizontal velocity, is 0.74 meters per second. And we're looking for time. So based off of the variables that we have, look at your two equations for finding time and see which one you can use. Well, the only one that'll work based on what we have is going to be 2 times dy over a, and then take the square root of that. And when you plug that all in, 2 times negative 1.25 divided by negative 10 gives you the square root of 0.25 seconds squared. But again, we're not finished. You can't ever leave an answer like that. You need to keep on going with the math and give me an actual number. When you do that, you get the time is equal to 0.50 seconds. And we add that extra 0 on at the end because we've got 2 sig figs over here, and so we want to keep 2 sig figs in our answer. I'm not going to be super picky about that though. Well, now look, I've got the same problem, but I've got a second part. How far from the end of the counter does it land? So we've got our same Vx, we've got our same dy. And what we're looking for is going to be our dx, our horizontal distance. How far from the end of the counter? So here's the end of the counter, and I want to know how far away. That's a horizontal measurement, a side-to-side measurement. So we've got the same given, a equals negative 10 meters per second squared. We've got our dy, negative 1.25 meters. Our Vx is 0.74 meters per second. We just found the time in the last question, so time is equal to 0.50 seconds, and we're looking for dx. Again, go back to your equations, and you'll see that the equation for horizontal displacement is Vx times t. That's a really easy calculation. 0.74 meters per second times 0.50 seconds gives you 0.37 meters. So what that's saying is this plate is going to fly off the edge of this counter, and then it's going to have this little parabolic trajectory down to the floor, and it's going to land on the floor, boom, 0.37 meters away from the edge of the counter. Last example problem here. A ball rolls off the edge of a table that is 0.97 meters high. The ball lands 0.65 meters from the base of the table. Calculate the ball's horizontal velocity as it left the tabletop. Now, I'm not going to draw a picture on this one because, frankly, I don't have the space on my slide. But again, I would encourage you to draw a picture if that helps you kind of keep track of what is a horizontal variable and what is a vertical variable. So we're going to go through our givens again. A is equal to negative 10 meters per second squared. We know that our dy is negative 0.97 meters. Again, negative because we're going down from the edge of the table down to the floor. We know that our dx is 0.65 meters because it's landing that far away from the base of the table. And we are looking for Vx. We're looking for horizontal velocity. Well, if you look at the equation for Vx, it's dx over t. Well, we're missing a piece. And this is going to be real common in your projectile motion problems. You're going to have to find time in order to plug that in and solve for whatever else you might be looking for. So we've got a t equals question mark as well. Well, let's look at our givens again. We've got a dy and we've got an a. So we can use 2 times dy over a, take the square root, to find our time. So when you plug all of that in, you get our time is equal to 0.4405 seconds. Then you can plug that back into your equation for Vx. So 0.65 meters divided by 0.4405 seconds. Do the math on that. Don't ever leave it as a fraction. And we get 1.5 meters per second. So 0.97 meter high table. We've got a ball rolling off the edge of the table at 1.5 meters per second, which means that it lands, boom, 0.65 meters away from the table itself. So now it's your turn. You're going to go through a practice quiz for vectors and projectiles. Make sure that when you're doing any sort of calculations that you've identified every single variable possible before you try and solve the problem. Always remember that you've got an automatic given with your acceleration. Remember that is vertical acceleration, negative 10 meters per second squared. And just be really careful keeping track of what's horizontal versus what is vertical.